Hi, this is Ana Douglas for ECE 530 Intro to Optics and Photonics. In this video, we will understand the difference between external and internal refraction. We will also describe the phenomenon of total internal reflection and estimate the incidence angle called a critical angle, in which the refracted ray has an angle of 90 degrees. So if you remember the first video of this module, we were discussing the reflection and the Snell law. So we know when an incident beam travels through a medium and transfer another medium, we're gonna have a reflected beam that has the same angle. So we have here theta 1, so the incident and the reflected beam are gonna be the same. But we also might have a refracted beam theta 2 that is referring with the refracted beam. And we can estimate the refracted angle knowing the refractive index between the two medium and the sine of the incident angle. Remember that every medium has a refractive index, so the refractive index is going to be the ratio of the light, the speed of the light propagating in vacuum or air or free space over the speed of the light in the medium, and that refractive index is always higher or equal than 1. So let's talk about external refraction. So external refraction is for the particular case where the refractive index of the first medium is smaller than the refractive index of the second medium. So if we go to the Snell law, we know that the refracted angle is going to be the inverse of the sine of n2 over n1. n1 over n2 sine of theta 1. And even we can go a little, we can make the approximation that the angles are small, so that means that sine of the angle can be approximated to the value of the angle. So theta 2 is going to be approximated to the ratio n1 over n2 theta 1. Why I want to do that approximation? Just to kind of see that if n1 is higher than n2, this ratio is going to be above 1. So that means that theta 1 needs to be smaller than theta 2. So the refracted rays or the refracted rays are closer to the normal. So when we think about the normal here, theta 2 is smaller than theta 1. And that's what we're going to define as the external refraction. Let me show you something about the linear behavior. The linear behavior means that we have values that they are really small. So this is kind of the linear behavior. The refractive index of both medias are the same. So that means that there is no actual bending. But we are close to the linear behavior for small values there, the refractive index, and then after all, this is kind of the behavior of the refracted angle for different values of the incident angles. So opposed to the external refraction, we find the internal refraction. So the internal one is for values is when the refractive index of the first medium is higher than the refractive index of the second medium. Again, we can make the approximation for small angles just to see that now theta 2 is going to be still approximated n1 over n2 theta 1, but because n1 is higher than n2, that's going to mean that now theta 2 is going to be higher than theta 1. Sorry about that. This is a 1 here. This means that theta 2 is higher than theta 1. So the refracted rays, or the refracted ray goes away from the normal. There is a particular case where the refracted angle is equal to 90. So let's talk more about this particular case. So we know that we are in the case where n1 is higher than n2, and therefore theta 2 is going to be higher than theta 1. But there is going to be a particular case that there is a particular case where theta 2 is equal to 90 degrees. So when we are saying the sine of theta, the sine of 90 degrees is going to be equal to 1. So we're going to define the critical angle. So theta c, this is the critical angle, and this is equal to the incident angle theta 1 that theta 2 is equal to 90 degrees. And that means that our refracted beam goes on the interface. So that's 90 degree means that here we have a 90 degree angle between them. So what is going to happen if we have a beam, an incident beam, that the so what's going to happen if the incident angle is higher than the critical angle? So in this particular case, what is going to happen is that our interface between the two medium is going to act as a mirror. So we don't going to have any refracted angle. We're just going to have only reflected ray. And we're going to obey the reflection law. So that means that with respect to the normal, the refracted angle needs to be equal to the incident angle. But this effect is going to happen when the incident angle is higher than the critical angle. So this phenomenon is called the total internal reflection, and this is the one that we observe in optical fibers. So optical fibers are optical elements that they guide the light between two medium. The medium are concentric glass cylinder called the core and the cladding, and the fact is that we have total internal reflection because the refractive index of the core is higher than the refractive on the index. So always that the value is higher than the critical angle, we're gonna have total internal reflection. Just to apply a little more about the total internal reflection, let's do this in-class problem. So we have a step index fiber that the refractive index of the core is 1.53 and the refractive index of the cladding is 1.39. And they want us to estimate the incidence angle, the acceptance angle in the air, such a way that we have a refracted angle between the core and the cladding is 90 degrees. So we are hitting the interface between the core and the cladding with an incident angle that is equal to the critical angle. So let me try to skate this as like this is gonna be my air medium, this is my normal, and here I have my incident angle, the light travels. So this is my acceptance angle, and now I'm gonna have my core right here. So I'm gonna have a refracted angle here. This is gonna be my theta 2, and then here I have my cladding medium, so I have my normal, and I know that I'm gonna have here my refracted. So here my angle here on the cladding, the refractive on the cladding, is equal 90 degrees, and that means that this angle that I have right here. This is my critical angle. So let's work it out, the math. So the first boundary I'm gonna have is my core cladding boundary interface. So I know that the refractive index of the core sine my critical angle, this is gonna be equal to the refractive index this is gonna be equal to the refractive index of the cladding. And now I know that I'm gonna have sine of 90 degrees, with this whole sine is gonna be equal to 1. So my critical angle is the inverse of the sine of n cladding over n core. So this is gonna be the inverse of the sine of 1.5 over 1.42. So my critical angle, my incident angles within the boundary of the core cladding, that's gonna be 71.2 degrees, right? So now what I want you to see is kind of this triangle right there. So I have sorry about that. So I have this triangle where this is my refractive angle between the air core, and this is right here is gonna be my critical angle. So I know that my refracted angle, like the sum of the angles in a triangle, is 180 and this is 90. So I know that my refracted angle, that's gonna be 90 minus the critical angle, so that becomes 18.796 degrees. So now that I have that angle, I can go to the boundary of air. So this is gonna be theta m, and now here I have theta 2. So this is core, this is air. So I'm in the boundary of air core. So I know that the refractive index of the air sine of my incident angle becomes equal to the refractive index of the core. And then sine of theta 2, but we already know that theta 2 is 18.795 degrees. So we can estimate the maximum angle as the inverse of the sine of n core over n air. N air, remember that is 1 sine theta 2. So if we plug here the values, n core equal 1.5, and then n air is equal to 1. Here we have 28.9 degrees. So I hope that this is helpful and you know more about the difference between external and internal reflection. Thank you.